So summarizing what we have seen, the differential equation for a damped spring mass system and the differential equation for an RLC circuit basically have the same form. And that form is constant times second derivative unknown function plus constant times first derivative plus constant times unknown function equals 0. So this is something we will study a whole bunch, and here's how I'm going to describe differential equations of this form. They're second order, you know what that means. Linear, you kind of know what that means, but I'm going to get into it. Differential equation homogeneous. Homogeneous. You might know what this means from linear algebra. Differential equation with constant coefficients. So let me describe each of these. Okay, so first, second order, that just means there are up to two derivatives showing up, with this coefficient here not being 0. So that one's pretty simple, second order. Constant coefficients is also pretty simple. Constant coefficients means these coefficients here are constants. No time dependence. So no t here, no t, no t. They're constants. Linear and homogeneous. So linear we have described before. So linear we have described in lecture 4, part 2. Lecture 4, part 2. And if this discussion becomes confusing for you, I would recommend revisiting that one and then coming back here. So I want to explain how this is a linear differential equation now. And then homogeneous has to do with the same kind of topic. So linear differential equation means it's a linear system in the following sense. Remember from linear algebra, you had these as linear systems. Matrix times unknown vector equals a certain vector. And then trying to solve means finding values for this vector to make this true. So now in this current context, what's playing the role of vectors is functions. You can actually treat them like vectors. They are living in a certain vector space. And what's playing the role of matrix is a differential operator, which I'm going to write down. And what's playing the role of the right-hand side, what's playing the role of vectors is functions. So the right-hand side is going to be also some function. In this case, I'm going to put 0 on the right-hand side to match up with this 0. And when I say it's a linear differential equation, what I mean is what's happening on the left-hand side, if you think of the left-hand side as an operator applied to x, applied to the function x of t, then that operator is a linear operator. So let's have a more close look at this. We're looking at something of this form. The left-hand side is this operation that's happening to x. Think of it as x becomes ax prime prime plus bx prime plus cx. So when x becomes this, what's happening to x? Like if x becomes x prime, then what would you say is happening to x? You would say d dt is getting applied to x, right? If x becomes x prime prime, then what would you say is happening to x? You would say the second derivative, d squared dt squared, is getting applied to x. So over here, with this complicated thing, what's happening to x? So if I want to write this differential equation as some operator applied to x equals 0, what is that operator, in other words? It is a times the second derivative operator plus b times the derivative operator plus c. So this operation on x equals 0. That's the differential equation. So let's call this here L. then the differential equation says L, so this is the part that I'm calling L here, the part in parentheses. L is a thing, it's not exactly a function in the traditional sense, like x of t is a function. L is sort of like an operation that eats functions, and it does stuff to functions. So when you apply L to the function x, you want to get 0. You're trying to find x's that solve Lx equals 0. Now, if you remember from linear algebra, ax equals b, that was the form of a linear system, right, where A is a matrix. What do you say about the linear system when the right-hand side is 0? When the b is 0, like ax equals 0, what do you call this? You call it a homogeneous linear system, right? Same deal here. So here we could have had another function on the right-hand side, not 0. So we could have had, like, you know, some function b of t or something. So that could have been here. We could have had b of t. And later we will do that. So we will eventually include a function here. That would be what you'd have to do to allow for there to be a power source in your RLC circuit, for example. Or if you want to have an explicitly time-dependent forcing function applied to your mass on a spring, you would have to put a function of t here. Then it would become non-homogeneous. But for now, what we're going to study has a 0 here, which means we're looking at Lx equals 0, where L is linear. And I keep saying linear, but I haven't proven that, or I haven't done anything to convince you of that. So why is this linear? Well, the meaning of linear is, and this is worth going back to lecture 4 part 2 if you've forgotten it by now. The meaning of linear is when you apply it to a linear combination, like say c1x1 plus c2x2, where x1 is a function of time and x2 is a function of time, and c1 and c2 are constants. If you apply it to a linear combination, then it should distribute. So this is what we mean by linear. This will distribute. So let me give you an example of something that wouldn't be linear. So here's a nonlinear second order differential equation. X prime prime times x prime equals 0. What would you call this left-hand side? If you tried to call this L, and if the way L works is that it sends x to x prime prime x prime, then L is definitely not linear. And I'm not going to get into showing it, because I think I did this kind of example back in lecture 4 part 2. I don't want to repeat so much, but I just want you maybe you can try showing it for yourself if you're interested. I just want to convince you that not everything is linear. Even very simple looking things like this do not have to be linear. But this is linear. And it would still be linear if I did this. If I made these coefficients time dependent. So instead of a, b, and c, a of t, b of t, and c of t. If I did this, this would still be linear. If I made these depend on time, this would still be a linear differential equation. So that's what a linear second order differential equation looks like. It looks like this. And it doesn't have to have 0 here. It could have a function of time. But if you want it to be homogeneous, if you want to use the word homogeneous, that means you've put 0 here. So hopefully that clarifies what is meant by linear and homogeneous. And if I allow these coefficients here to depend on time, then I would say I do not have constant coefficients. So the word constant coefficients here is referring to the fact that a, b, and c do not depend on time. Now, what you have here, so slightly unrelated point now that I want to make. Look at these two differential equations. They both have that form, ax prime prime plus bx prime plus cx equals 0. But the things playing the role of a, b, and c are different constants. But these constants have physical meaning. So since we have the same differential equation, like here and here we have the same differential equation, the spring mass system and the RLC circuit, same differential equation. Since we have the same differential equation, we have the same dynamics. We're going to have the same given initial conditions, like x of 0 and x prime of 0, or q of 0 and q prime of 0. If you make those the same, then you're going to get the same behavior. You'll get the same predictions because it's the same differential equation. So there's like a pretty exact analogy going on here. And it's just that the constants are coming from different sources. So it's interesting to look more deeply at, oh, I'm sorry, there's a typo here. This should be x prime. So it's interesting to look more deeply at what's getting related. Like, apparently K, the spring stiffness, is a lot like 1 over the capacitance. Interesting. Apparently gamma, the damping coefficient, how strong the friction in the spring is similar to resistance in the circuit. And apparently mass is similar to inductance of the inductor. So one way to describe this is, one way to describe the spring stiffness, the spring constant K, is it's kind of like describing the ability of the spring mass system to store energy in the compression or expansion of the spring. So this, in some sense, does describe energy storage. You know, if you make K large, then more energy is stored in the system when the spring is displaced by the same amount. For larger K, same amount of displacement leads to more potential energy there. So that's one way to think about this. And capacitance, the 1 over capacitance can be apparently thought of the same way. So this is like a energy storage term in the differential equation. And continuing with the analogy, gamma represents loss of energy due to friction, right? This is like the friction term, friction in the spring. So this represents energy that gets lost from the system. And well, R really is a very similar kind of thing. The resistor does serve to dissipate power from the circuit. So this does represent energy loss. And here, mass, so when you're talking about Newton's second law, mass sort of represents the phenomenon of inertia, right? That, you know, a very massive thing is harder to move. It wants to keep its velocity more. So apparently inductance is a lot like inertia, but for a circuit. So you can think of inductance as representing how hard it is to accelerate Q, or how hard it is to, if you just take derivatives everywhere here, then Q becomes I, the current in the circuit, how hard it is to accelerate the current. Okay, so hopefully now you are convinced that it's worth studying these kinds of systems, but I mean, just partly because when you're looking at this just as a pure math problem, it captures multiple different physical situations and establishes a nice analogy between them. But in the next video, I hope I can convince you further that this goes well beyond just these two specific physical systems.